11th B. Collisions. 11.7 Linear Colisions. We have discussed the conservation of momentum when internal forces separate objects within a system. Now, let us discuss the conservation of momentum of colliding bodies. In general, the same principle applies as long as we consider the colliding objects as parts of a single system. The momentum of the system is conserved unless an unbalanced external force acts on the system. The air track shown in Figure 11-5 is a traditional physics laboratory apparatus that demonstrates conservation of momentum in collisions. The track is pierced by hundreds of holes, through which air flows to form a nearly frictionless cushion of air to support Y-shaped gliders. The gliders move in a linear path along the straight rack. Suppose glider 1 with mass m1 on the left part of the track is given a velocity of v1 toward the right. Glider 2 with mass m2 is at rest to the right of m1. We will consider the system to include both m and m2. See Figure 11.6a on the next page. There are no external unbalanced forces on the system. Therefore, the total momentum of the system is conserved and delta P total equals 0 kilograms per meter per second. What happens when m1 collides with m2? We know that the total momentum before the collision is P total BFR equals P1 BFR plus P2 BFR, where the subscripts 1 and 2 identify the properties of gliders 1 and 2, respectively, and the subscript BFR identifies the properties before the collision. The total momentum of the system after the collision is P total aft equals P1 aft plus P2 aft, where the subscript aft identifies the properties after the collision. Since no external force is exerted on the system, the momentum of the system before and after the collision must be the same. P total BFR equals P total aft. If we expand these expressions, we can see how the individual momenta change, but the overall system momentum is unchanged. P1 BFR plus P2 BFR equals P1 aft plus P2 aft. P1 BFR, P1 aft equals P2 aft. P2 BFR, P1 aft, P1 BFR equals P2 aft, P2 BFR. M1, V1 aft, V1 BFR equals M2, V2 aft, V2 BFR. M1, V1 aft minus V1 BFR equals negative M2, V2 aft minus V2 BFR. This relationship can be summarized in the equation. Delta P1 equals negative delta P2, 11.8. Before the collision, M2 is at rest, so V2 BFR equals 0 meters per second. Therefore, M1 V1 aft M1 V1 BFR equals minus M2 V2 aft, 11.9. We do not know either V1 aft or V2 aft. Since there are two unknowns in equation 11.9, we cannot solve it. We need another equation involving the unknowns before we can find their values. This requires a closer look at the kind of collision that occurred. 11.8 Collision modes. Objects may collide in one of three ways or modes. In an elastic collision, only conservative forces act. Therefore, total mechanical energy S conserved. This is a strictly theoretical mode of collision, but many real systems approach this condition, such as the collision of billiard balls rolling on a hard, smooth surface, or the collision of air molecules. In a partially elastic collision, one or more of the colliding masses is deformed, changes its shape, but the masses rebound away from the collision. The material deformation converts some of the system's kinetic energy to work and elastic potential energy, and to thermal energy, sound, or other non-mechanical energy. Most real collisions are partially elastic. In an inelastic collision, the colliding masses stick together. The collision converts a large portion of the initial kinetic energy to work on the parts of the system. Therefore, kinetic energy is not conserved. Examples of such a collision are a bullet embedding itself in a tree and a scoop of ice cream falling to the floor. 11.9 Elastic collisions. Let's suppose that the collision between the gliders on the air track is elastic, and x is positive to the right. Kinetic energy is conserved. Therefore, the following relationships are true. K total BFR equals K total ATS and 1/2 N 1v1 square. BFRX plus 1/2 M 2v2 square. BFRX equals 1/2 M 1v1 square. Aft x plus 1/2 M 2v2 square. Aft x. In this example, V2 BFRX equals 0 meters per second. So, 1/2 M 1v1 square BFRX equals 1/2 M 1v1 square after x plus 1/2 M 2v 2 square after x. 11.10. Earlier in the discussion, we obtained equation 11.9, M1v1 aft. M1v1 BFR equals minus M2v 2 aft. Since the problem is one-dimensional, we can rewrite equation 11.9 in scalar component notation as M1 v1 aft x minus M1 v1 BFR x equals minus M2 v2 aft x. 1.11. Combining equations 11.10 and 11.11. We can solve for v1 aft x and v2 aft x. We find that v and afts m and minus m 2 over m and plus m2. v and BFR x 11 12. v2 aft x equals 2 meters 1 over meter 1 plus meter 2. v1 BFR x 11.13. These equations hold for any elastic collision, where 22 moving mass m1 collides with a resting mass m2. If v1 aft x is negative, it simply means that m1 rebounds from the collision with a speed v1 aft. The moving glider stops, and the stationary glider moves off with the velocity that mi originally had. The momentum of each object has changed in the collision, but the total momentum of the system of objects has remained the SARN. The moving man barely slows down, while the stationary drum shoots off at nearly twice the man's original velocity. This is true for elastic collisions between a very large moving mass and a relatively small stationary mass. Once again, the moment of the two objects is very different after the collision, but the total momentum of the system is unchanged. The cork bounces back with nearly its original speed, while the stone hardly budges to the right. This result is typical of an elastic collision of a small moving mass with a large stationary mass. If the stone had been immovable, attached to an extremely large mass, the cork would have bounced back with exactly its original speed. We assume that this is the case when we discuss an elastic collision with a solid wall. 11.1 Inelastic collisions. We have discussed idealized elastic collisions, but what about the other extreme, idealized inelastic collisions, where the colliding objects stick completely together following the collision? Going back to the air track example, suppose that glider M2 has tacky glue on the end facing glider M. When M collides with it, the gliders stick together. Therefore, both gliders must have the same velocity after the collision. V1 aft x equals V2 aft x equals V aft x. Equation 11.9 becomes M1 V1 BFR x equals open parenthesis M1 plus M2 close parenthesis V aft x open parenthesis 11.14 close parenthesis. Since we know all these quantities except the final speed of the system, we can find VAT x without using a second equation. In an inelastic collision, kinetic energy is not conserved because some of the initial kinetic energy is converted to work to accelerate the stationary object and to decelerate the moving object to the final velocity of the combined system of objects. After absorbing the work, which is internal to the system, some of the energy is also manifested as other forms of energy, such as thermal energy, sound, or light. 11.11 Ballistic Pendulums. An experimental device that depends on completely inelastic collisions is called a ballistic pendulum. It is normally used to determine the energy of projectiles, such as military and civilian bullets. Indirectly, this information can be used to find projectile velocity. A ballistic pendulum consists of a uniform block of a dense material attached to one or more pendulum arms. Figure 11-10 shows a typical ballistic pendulum. The projectile to be tested impacts the pendulum and embeds itself in the block. The bullet converts essentially all of its kinetic energy into pendulum potential energy as the pendulum rises. An angle indicator records the maximum angle attained by the pendulum arm, and engineers are then able to calculate the kinetic energy and velocity of the projectile at impact. 11.12 Two-dimensional collisions. Most collisions occur in 2 or 3 dimensions. Momentum is conserved 2 and 3-dimensional collisions as well as in 1-dimensional collisions, but the equations are more complicated for more dimensions. An excellent apparatus for demonstrating 2-dimensional collisions is an air table, very similar to an air hockey table. Its surface has numerous holes through which air flows to suspend pucks of various masses and to permit nearly friction, less motion. In Figure 11-12a, puck M1 approaches the stationary puck M2 from the left with velocity v1 BFR. Puck 1 elastically strikes puck 2 off-center in caroms with a velocity v1 aft. At the same time, M2 rebounds with velocity v2 aft. Momentum is conserved, and equation 11.8 holds true. Delta P1 equals negative delta P2 since v2 BFR equals 0 meters per second. Collecting terms for momenta before and after the collision, M1 v1 BFR equals M1 v1 aft plus M2 v2 aft. In order for momentum to be conserved, the x component of the momentum before collision must equal the sum of the x components afterward. The same is true of the y components, but M1 v1 BFR is only in the x direction. It has no y component, while M1 v1 aft and M2 v2 aft both have y components. This difficulty is resolved by Figure 11.12b. The y components of the two momenta after the collision exactly cancel each other. To find the final velocities of objects involved in a two-dimensional collision, obtain the components of their velocities from the x and y components of their momenta. When two identical particle-like objects collide elastically, the post-collision angle between the objects' paths is exactly 90 degrees. As the amount of deformation in one or both objects increases and the collision becomes more inelastic, the angle becomes smaller. For completely inelastic collisions, the rebound angle is 0. See the illustrations in Figures 11-13a and b. 11.13 Using changes in impulse and momentum to solve problems. Christians have biblical reasons to design vehicles that will preserve and protect human life. Genesis 9:6 Injuries and fatalities in car accidents are reduced by reducing the impulsive forces on the passengers' bodies. If a person's body can be cushioned, our parts of the car can compress to absorb energy. The magnitude of the impulse can be decreased by stretching out the time in which the change in momentum takes place. Intelligently designing cars to accomplish this requires that engineers understand the forces and times involved in a collision. But how can they make these kinds of measurements to guide technological development? In order to design cars and safety features for maximum effect, engineers need feedback about the susceptibility of the human body to forces and impulses. Make seatbelts or airbags too stiff, and they can cause injuries. Make them too soft, and they may not provide adequate protection. This is where crash test dummies enter the picture. Crash test dummies were first used in the 1940s to test ejection seats in military fighter aircraft. Before this, engineers resorted to using cadavers. When the American automaker Ford started including seatbelts in its cars, auto engineers began using dummies that better resembled humans in weight, form, and reactions to external forces. Automaker General Motors has developed a whole family of crash test dummies that represent different sizes and kinds of people, including adults, children, infants, and even pregnant women. Different dummies are used for different types of tests, such as rear impacts, frontal impacts, side impacts, and rollovers. Dummies used for these tests contain sensors in different places such as the chest, head, neck, back, legs, and pelvis. Some have specific designs to measure the possibilities of injury to the back and neck. These sensors are one of 3 kinds: load sensors, motion sensors, or accelerometers. Load sensors measure the force exerted on a certain part of the body. Motion sensors measure how much a part of the body, like the chest, is compressed or moved. Accelerometers measure how fast a certain part of the body changes speed. These sensors collect data and send it to specific input channels on a computer. Automated algorithms process the data to compute the likelihood of injury by comparing the impulse generated to the susceptibility of various joints and body parts to injury. Usually, this data can be synchronized with video and high-speed photographs of the test collision. Thanks to collision tests using crash test dummies, many car parts, including airbags, seatbelts, padded dashboards, sturdy fenders, and collapsible steering columns, have been designed to provide people with the best possible protection compartment, are being designed to fail safely, so they do not add to the severity during a car collision. Other aspects of the car, like the fuel system and the engine of the collision, by starting a fire or allowing the engine to penetrate the passenger compartment.